Welcome to Designing Data Flows in Microsoft Azure. My name is Thomas Mitchell, and I'll be taking you through this course on designing data flows in Azure. I'm an Azure content author at Cloud Academy, and I have over 25 years of deep IT experience, several of those with cloud technologies. If you have any questions, feel free to connect with me on LinkedIn or send an email to support@cloudacademy.com. This course is intended for IT professionals who are interested in earning Azure certification and for those who need to work with data flows in Azure. To get the most from this course, you should have at least a basic understanding of data flows and what they are used for. In this course, we're going to review the features, concepts, and requirements that are necessary for designing data flows and how to implement them in Microsoft Azure. We're also going to cover the basics of data flows, common data flow scenarios, and what all is involved in designing a typical data flow. By the time you complete this course, you'll understand key components that are available in Azure that can be used to design and deploy data flows. You'll also know how they all fit together. We'd love to get your feedback on this course, so please give it a rating when you're finished. If you're ready to learn about designing and documenting data flows in Azure, let's get started. Throughout this course, we're going to talk about the basics of data flow, starting with the fundamentals. We'll talk a bit about how you can provide data flow solutions using Microsoft Azure services. We're also going to discuss a few reference architectures as well, so we can kind of pull everything together. We'll also cover some common data flow scenarios so that you can better understand the requirements, the technologies, and the core data flow pipeline. These basic concepts are important because businesses need to know where they are performing well and where they are performing poorly. They need to ask hard questions about where the business is and where it's headed. Such answers can be pulled from the data that's collected by the business itself. There may even be cases where additional questions about the business might be asked in the future. As such, it's critical to keep raw data around for some time so any of these future questions can be answered. The concept of data flow encompasses the initial ingestion of data, any required transformations, storage of the data, and then ultimately analysis of the data. Data flow is essentially about what needs to happen with the data in order to meet business requirements and how it can be used to answer questions about the business. As such, it's important to get this right. Without the right data flow, a business may not be able to find answers that it needs today, let alone answers it might need in the future. In this lecture, let's talk a bit about data flow scenarios. Specifically, I want to talk a bit about batch processing, stream processing, and hybrid. I also want to discuss ETL versus ELT, and schema on read versus schema on write. By better understanding common data flow scenarios, you can be better prepared to design and document data flows in production. Batch processing is useful in cases where there is a large amount of data quickly moving into a system. Data such as this, processed on a schedule, is considered to be batch processed. Generally speaking, such batch processing jobs will inherently produce delays, and because such data is processed on a schedule, it's not real time. An example of batch processing would be a case where data comes in over the course of a day. Think of a retail store at the mall. Throughout the day, sales data comes in fast and furious. At the end of the day, the retailer might run a batch process that analyzes all the sales data for that day. The retailer will typically throw a bunch of compute power at the data that needs to be processed in a single batch at the end of the day, or maybe even overnight. The data is processed, transformed into a usable format, and then stored for later access. The data flows from ingestion to transformation to storage. It's a pretty typical case of batch processing. Stream processing of data refers to the analysis of data as it's received. While it might not necessarily be real-time processing, Delays are typically sub-second. As data comes into the pipeline, analysis is performed and results are generally available within seconds or even milliseconds. Processing continuous data in stream requires technology that can handle this. Technologies like Lambda are available to provide this type of stream processing. Lambda, incidentally, supports both batch and stream processing. Stream processing, or even batch processing for that matter, will often lead to an eventual ETL process or an ELT process. ETL refers to extract, transform, and load, while ELT refers to extract, load, and transform. Both concepts refer to the process of obtaining data, extracting it from its source, and then transforming it. The transformed data is then stored for analysis later. ETL transforms the data before loading and storing it. ELT loads collected data before transforming it, which usually means data can be handled at a greater scale. In a hybrid processing data flow scenario, data that's processed, used, and stored is generally distributed among cloud and on-prem systems. As such, the data flow itself will often travel from on-prem to cloud and maybe even vice versa. As such, it's important to think about bandwidth, especially when dealing with a data flow that moves data from on-prem up to the cloud. It's important to assess the size of the pipe, the latency, and the cost implications of data ingress and egress to and from the cloud. A common hybrid scenario is one in which data is ingested from applications and systems that rely on-prem, and then stored and processed and maybe even transformed in the cloud. When designing a hybrid data flow that sources data from on-prem devices, application, forms, or really any other type of on-prem source, a key consideration is how the connection from the on-prem environment to the cloud is constructed. While a site-to-site VPN might be sufficient, latency issues may dictate that an express route be considered instead. Whether you use ETL or ELT, both patterns are commonly used to form most data flows in production. As mentioned previously, the ETL, or extract, transform, and load process, begins with extracting data from one or more systems. The extracted data might be in the same format, or it can be in all different formats. Once the data is extracted, it's transformed into some usable format, typically in memory. The data is then stored so that it can be queried later. As such, ETL is considered schema on write, because the data is first transformed into some standard format or schema before it's written to storage. The ELT process, or extract, load, and transform process, essentially replicates data to storage as is. Only after the data is written to storage is it transformed into a usable format. This is referred to as schema on read because there's no schema enforced on the data during initial ingestion. Instead, the data is transformed after it's been stored and while it's being used. When considering ETL versus ELT, the main driver generally comes down to scale. Using ETL requires data to be transformed before it can be loaded. This means that there's lots of compute power needed. As such, this can negatively impact the ability to process large amounts of data. Using ELT instead separates data ingestion from the transformation process. What this does is allow huge amounts of data to be ingested and loaded before it's transformed. By breaking the process apart in ELT, it's possible to ingest lots more data than with ETL. You can essentially ingest data as fast as it's written. Ultimately, if scale is a concern, ELT is the preferred strategy over ETL. In this next lesson, we're going to touch on the data lifecycle. It's important to understand the data lifecycle because the different stages of the lifecycle will affect data flow. Overall, there are really 5 key stages in the data lifecycle. You have the initial collection of data, the preparation of that collected data, the ingestion of the data into storage, processing or transformation of the data into usable form, and then you have analysis of the transformed data. During collection, data is acquired from other processes or maybe even user input, Such data might be in varied formats or it may be unstructured. Preparation of the collected data may or may not happen next, depending on the process. In cases where ETL is in play and data needs to be transformed before it is ingested or loaded, there is certainly a preparation step that occurs. Once data has been collected and prepared, it needs to be ingested into storage. In the context of this discussion, the data would typically be ingested into cloud storage. Once the data has been ingested into storage, it needs to be processed or, if ELT is being used, transformed into a usable format. Finally, once the data has progressed through all previous stages of the lifecycle, it can be analyzed and interpreted. With the typical data lifecycle in mind, you then need to think about some things as you design a data flow that encompasses this data. You need to think about where the data is coming from and in what format it's arriving. You need to determine how it needs to be transformed, and if so, how that needs to be done. You need to think about the ultimate destination of this data and its analysis. Where is the data going, and what questions does it need to answer? Only after considering all of these concepts can you begin to formulate a data flow plan and come up with data flow requirements. Before designing a data flow, you need to determine what data flow requirements there are. Determining data flow requirements requires you to ask and answer lots of different questions. You need to ask lots of questions up front because when you transform your data, you're often going to keep only the information that you care about, dumping the rest. If you don't think everything through, you might very well dump data that you don't care about now, but might care about later on down the road. In this lecture, we're going to discuss some of the key questions and considerations when determining data flow requirements. So what questions need to be asked? Well, for starters, you need to understand the source or sources of the data and what the data is exactly. You'll need to determine what format the data is in and if it's coming from another database. Is it XML? Is it JSON? Is it unstructured images? As you can see, lots of questions about data format. After sorting out the source and format of the data, you need to identify any security-related issues. You need to identify who needs to access the data and what they can do with it. Access controls will need to be kept in place throughout the lifecycle of the data. This is most important when pulling data from multiple sources, because when you do, the source data is likely protected. Dumping all of this data into a shared repository suddenly makes the data available to people that might not need access to it. As such, it's critical that you understand the security requirements of the source data and that you retain that security once the data has been collected. Along with security considerations, you also need to account for auditing requirements. You need to determine if there are auditing or logging requirements for the collected data. If there are auditing requirements on the data, you might be able to use metadata, such as creation data, batch data, modified dates, and such, to track the data as it's loaded. Logging requirements, if there are any, can be addressed with operation counts, insertion counts, stuff like execution times, and even success or failure information for data loads. Storage retention requirements are also an important consideration. When designing a data flow, you need to determine if you need to or want to store the data forever. You also need to determine if the data needs to be stored in its raw format. The answer to this question is often yes, because if you only keep the data that's been transformed or processed, you may find yourself with unanswerable business questions later because the data that answers those questions was trimmed during the processing stage. You'll also want to determine whether there are retention policies that affect how long data is retained. Are there certain policies or laws that require data to be retained indefinitely or for a specific amount of time? It's an important consideration. Another important consideration is GDPR. Does GDPR even apply? Is there certain data that needs to be removed? Is there a requirement that certain data be removable in the future? All important questions to ask. Another key consideration when designing data flows is metadata. If you are going to be analyzing the data eventually, what metadata, if any, is necessary to facilitate that analysis? Additionally, you should consider what business intelligence tools are going to be used to analyze that data, because this will often determine in some part how that data is stored and in what format it's stored in. As you work through all the data flow design requirements, it's important that you also consider existing skill sets that are available. Because there are numerous technologies that come into play when designing and deploying a data flow, it makes sense to consider whether you have the in-house skill sets to support what you're designing. Think about it. If you're going to design a data flow that leverages Python or T-SQL, what good is it if there is nobody in the organization that knows Python or T-SQL? When deciding on what technologies to leverage in your data flow design, think about your team and what skill sets they possess. You might also consider using pre-existing packages that you already have. For example, if you're already using SQL analysis services and SSIS packages, you probably already have data flows and controls defined. It might make more sense to just bring those pre-existing solutions to the cloud, instead of reinventing the wheel with technologies that are foreign to your team. As you define all requirements for your data flow design, think about interdependencies of all the different components. This is important because you're going to need to make all these interdependent technologies work together, similar to that of an orchestrator of a symphony. If you can't make these technologies work together, you have no data flow. So, why should the cloud be used for data flow? Well, for starters, a key benefit of using the cloud for data flow is the fact that you don't have to worry about setting up or maintaining DMZs. Instead of needing to figure out what devices need to be open to the internet and which ones don't, the cloud kind of serves as a natural barrier, I guess you could say. So you don't have to worry about what ports do and do not need to be opened. When deciding how to leverage the cloud for data flow, it's important to consider the usual suspects, like cost, speed, latency, etc. Pulling data into Azure isn't going to incur any costs because it's considered ingress. However, pulling that data out later on is going to incur some kind of cost because it's egress. It's also important to consider latencies and bandwidth for both moving data to Azure and from Azure. With that said, leveraging ExpressRoute and peering ensures data travels through a private connection, which would maintain a steady and lower latency than if it was traveling over the public internet. Other benefits to the cloud for data flow processing include the number of services that are available to facilitate the data flow process to begin with. Leveraging functionality that's available as platform as a service allows you to essentially hit the ground running. Simply use the services that you need to design and manage your data flows without any worry about maintenance of the platform or services. The amount of work necessary to get up and running is minimal. To add to that, with such a wide array of services available, you're likely to have access to technologies that you simply wouldn't have access to on-prem. Stuff like machine learning and artificial intelligence would typically fall into this bucket. Leveraging the cloud provides elasticity as well. It allows you to scale almost infinitely if necessary. This isn't something that's easily accomplished on-prem. Cost and time would quickly become barriers to doing so. Instead, the cloud offers the ability to scale up and down as required, while allowing you to pay only for the services and resources that you use. This is especially helpful when dealing with uneven or inconsistent workflows that need to be processed. These benefits, however, will obviously vary on a service-by-service basis. Because data flow will rarely consist of a single component, in this lesson, I wanted to touch on the collection of components and considerations that are necessary when designing a data flow. Let's start with infrastructure as a service versus platform as a service. When designing a data flow in Azure, you need to consider that almost any service that will be part of the data flow is likely available in Azure as an infrastructure as a service-based solution. Generally speaking, this would be mostly virtual machines. What this means is that you could very easily lift and shift your resources from an on-prem environment to Azure. However, by doing so, you also burden yourself with all of the support goodies that an on-prem solution offers, including patching, antivirus, management, etc. However, if you move to a platform as a service-based solution, you're going to reduce or eliminate those tedious management and support tasks for your data flow solution, while also improving functionality and scalability. As such, In cases where there is a platform as a service based solution available, the general rule of thumb is to leverage them whenever possible. An example of this would be to leverage Azure Data Factory instead of using SSIS from SQL. When it comes to HA and DR, your data flow infrastructure is no different from any other IT solution. You need to ensure the availability and resiliency of it, which, by the way, takes us back to infrastructure versus platform, because leveraging platform as a service-based solutions, when possible, much of the necessary HA is going to be provided by the service itself, which removes it from your plate for you to deal with. DR, however, is a slightly different animal. For starters, when thinking about DR, you might find yourself wondering what DR you actually need. For example, instead of deploying an actual engineered DR solution, your actual solution might be as simple as recreating any resources that experience an issue, especially in the case of any compute or processing resources that are in play. Ultimately, HA and DR solutions will rely largely on how much infrastructure as a service you're using and how much platform as a service is in play. Now, while HA and DR might be less of a concern, either due to the intrinsic availability of platform as a service offerings or the ability to easily rebuild compute and processing infrastructure as a service resources, data protection is critical. When considering data protection, for data being processed in your data flow, you need to think about where the data is stored and if there is replication available. Network bandwidth and network latency are two key considerations when designing a data flow, especially when data is flowing from an on-prem environment to the cloud and vice versa. Sure, moving data within the cloud or moving data from on-prem to on-prem is generally not an issue. However, when you start traversing both environments with large amounts of data, latency and bandwidth becomes important. To address potential latency issues between on-prem and cloud, you might want to consider an express route, because express route offers the ability to maintain a consistent latency. As far as bandwidth goes, you can typically purchase any bandwidth you need. You just need to be cognizant of what you need. This is obviously based on the amount of data you'll be moving to and from the cloud, and of course at what velocity. Speaking of velocity, you'll also want to think about how you can automate processes such as scaling, scheduling, and even triggering processes. And of course, let's not forget about backups and monitoring. If you're dealing with data, you need to consider a backup strategy that can protect the data that you're dealing with. The ability to effectively monitor the entire solution as well as the individual pieces of the data flow from start to finish is also important for ensuring a smooth data flow. Another key consideration when working with data flows is control flow. Think about what components or services are going to be ingesting the data initially, what components are going to process or transform the data, and what processes are going to write the data to its destination storage. Security is another key consideration when designing a data flow. Because you're dealing with data, it should be a no-brainer that the data needs to be secured. It's important, especially in cases where data is coming from multiple sources, that people don't have access to data that they shouldn't have access to. That being said, it's critical that ACLs are maintained. As far as pricing goes, because money is no object is typically reserved for the mega rich, the cost of things is always going to be a consideration. The best way to deal with cost and pricing is to determine what the needs are versus the wants as they relate to your data flow solution. With that information in hand, choose the cheapest solution that meets all your needs. So as you can see, there are quite a few components and considerations that you need to think about when designing a data flow. When designing a data flow, storage is a key piece of the flow. As such, it's important to consider what options are available. In this lesson, we're going to look at Azure Storage, the blob storage offering in particular. Because blob storage offers multiple tiers, including premium, hot, cool, and archive, data storage costs will vary widely, depending on the tiers that you need or use. Obviously, data stored and accessed in the premium tier is going to result in the best performance and lowest latencies. Of course, it's also going to be the most expensive. The hot tier offers good performance for data that will be accessed frequently, but it's at a lower cost than premium. For infrequently accessed data that still needs to be available with no delay, the cool tier is a good fit. The archive tier, however, should be reserved for data that needs to be kept, but when needed, isn't needed immediately. As you move down from premium to hot to cool and then to archive, data storage and access costs are going to be adjusted to reflect the intent of the particular storage tier. The premium and hot tiers charge more for access since the data needs to be at the ready, while the cool and archive tiers charge less for access since the data is less readily available than the other tiers. Blobs will ultimately be the cheapest storage option available to you for storing data as part of your data flow. You essentially pay for storage only, no compute. Your storage costs will be determined by how much data you're storing and in which tier you are storing it. A single blob can host upwards of 5 terabytes, and a storage account can host up to 2 petabytes. They are a great choice for housing large amounts of data. This makes them perfect for initial data ingestion prior to processing it. And because blobs are built for unstructured data, they're great in cases where ELT is involved because you can really store just about anything in them, including media, video, images, and even CSV files. Blob storage is also a good choice for keeping raw data around long term due to its cost. As such, you can leverage it to cheaply store your raw data to reprocess it later if and when new questions about the business come up. In this lesson, I want to touch on Azure Data Lake Storage Gen 2 in particular. While Gen 1 provided a Hadoop-compatible file system that was intended for large-scale analytics, Gen 2 has upped the ante by incorporating Azure Blob Storage. It actually rides on top of it, to be exact. As a result, Azure Data Lake Storage Gen 2 offers the analytics performance of an HDFS-compatible file system while also offering tiering and data lifecycle management features of blob storage. Other features and benefits now available in Gen 2 as a result include data security, data durability, and replication options that weren't available before. With Azure Data Lake Storage Gen 2, you have access to not only the Azure Data Lake Gen 2 file system APIs, but also to the Blob REST APIs. As a result, you can interact with data in different ways. The best part about it is the fact that enabling all this cool functionality is as simple as changing a setting in the storage account. Instead of needing to provision a new service and maintain a new service, all you need to do now is enable it on the storage account. A key feature of Data Lake Storage Gen 2 is the hierarchical namespace that's added to blob storage. With a hierarchical namespace, objects and files are organized into a hierarchy of directories, which results in much more efficient data access. For example, renaming a directory becomes a single metadata operation on the directory being renamed, instead of a process that enumerates and processes all objects that share the name prefix of the directory. Other key features of Azure Data Lake Storage Gen 2 include Hadoop-compatible access and a security model that supports ACL as well as POSIX permissions, including some extra granularity that's specific to Data Lake Storage Gen 2. With an ABFS driver that's optimized for big data analytics, data access is improved. And because Data Lake Storage Gen 2 offers low-cost storage capacity as well as low-cost transactions, the service is cost-effective. In the next lesson, I'll show you how to provision an Azure Data Lake Gen 2 enabled storage account. To create an Azure Data Lake Storage Gen 2 enabled storage account, you're going to need a resource group that's going to act as the logical container for your storage account or any of your other Azure resources. I've already created a resource group called Azure Course here. To take advantage of Data Lake Storage Gen 2 features, we're going to need to create a storage account as a storage V2 type. It's a general purpose V2 storage account. When we name our storage account, we need to make sure that the name is between 3 and 24 characters, and it's got to be unique across the entire Azure landscape. So as you can see here, I'm in my resource group that I provisioned earlier. And what we're going to do is deploy our Azure Data Lake Storage Gen 2 enabled storage account within this resource group. To create our new Data Lake Gen 2 enabled storage account, we simply click Add up here at the top to create a new resource, and then we search for storage accounts. After selecting the storage account option in the list of results, we have to deploy an actual storage account. Don't be tempted to select the Data Lake option, because as you can see here, this Data Lake option is for Gen 1. We're deploying a Gen 2 enabled storage account. So we'll go ahead and click to deploy a storage account. After selecting the storage account option, we can simply go ahead and click Create to begin the deployment of the storage account. We need to select the subscription and resource group that we're going to deploy our new storage account to. In this demonstration, we're going to deploy to our pay-as-you-go subscription and in our Azure course resource group that we deployed earlier. I'm going to give my storage account a unique name here. Again, this needs to be unique across the entire Azure landscape. And for this demonstration, I'm going to deploy to the West US 2 location. When deploying our storage account that's going to be Data Lake Gen 2 enabled, we can leave performance, account kind, replication, and access tier options at their default values. We just want to ensure that we have the right subscription selected, and then we can click Next Advanced. We can leave the values under security and virtual networks set to the default options. But in the Data Lake Storage Gen 2 preview section, we need to turn on hierarchical namespace by setting it to enabled. After doing so, we simply click Review and Create to create the new storage account. When it completes, the new Data Lake Storage Gen 2 enabled storage account is now provisioned. As far as big data goes, unorganized raw data is going to often be stored in multiple storage systems, including relational and non-relational systems. The raw data on its own doesn't have much context, nor does it offer any meaningful insight. As such, it requires services to orchestrate and operationalize processes that can refine that data and convert it into useful business information. Azure Data Factory is an Azure offering that's built for complex hybrid ETL, ELT, and data integration projects. To illustrate the usefulness of Azure Data Factory, consider a casino that collects petabytes and petabytes of game logs from its slot machines on the floor. The casino needs to analyze these logs in order to gain insight into customer gameplay, customer demographics, and other useful information. The casino wants to identify reward offers that match the players and develop new games that drive growth and provide a better experience to its players. In order to analyze its gaming logs, the casino needs to leverage data such as customer info, game selection info, and marketing campaign info that is hosted in their on-prem data store. The casino wants to utilize this on-prem data, combining it with additional information that it has in a cloud data store. To extract meaningful information from this data, the casino needs to process the joined data by using a Spark cluster, such as Azure HDInsight, and then it wants to publish the transformed data to a cloud data warehouse, such as Azure SQL Data Warehouse. Doing so allows the casino to build a report on top of the data. The casino wants to automate the workflow, monitoring and managing it on a daily schedule. The entire data flow process needs to kick off when files land in the blob store container. For this example, Azure Data Factory can be leveraged because it's a cloud-based data integration service. It allows organizations to create data-driven workflows in the cloud for orchestrating and automating data movement and for data transformation. By leveraging Azure Data Factory, the casino can create and schedule pipelines or data-driven workflows that can ingest data from different data stores. Azure Data Factory can process and transform the casino's data by using several different compute services, including Azure HDInsight, Hadoop, Spark, Azure Data Lake Analytics, and even Azure Machine Learning. The output data can then be published to a data store like Azure SQL Data Warehouse, where BI applications can consume it. When all is said and done, Azure Data Factory allows the casino to organize their raw data into meaningful data stores and data lakes for better business decisions. In this first demonstration, we're going to create an Azure Data Factory. And what we'll do is we'll start the Data Factory user interface so that we can create a pipeline in the upcoming demonstrations. To create the Azure Data Factory, you need to use either the Edge browser or Google Chrome. At this time, the Data Factory UI is only supported on Microsoft Edge or Google Chrome. As you can see on your screen here, I'm in my Azure portal and I'm in my Azure Course resource group. To create the Data Factory, I simply click Create a Resource, and then I can scroll down to Analytics. Under Analytics, I'll find Azure Data Factory. So we'll select Azure Data Factory and begin the process here. On the new Data Factory screen, we're going to give our Azure Data Factory a name. The name that we give it needs to be globally unique. What this means is it needs to be unique across the entire Azure landscape, not just within your own tenant or subscription. So I'm going to call this My Data Factory and then give it a suffix. We then need to tell it what subscription to deploy to, and we're going to use the pay-as-you-go, and then we'll use my existing resource group called Azure Course. We're offered 3 different versions, version 1, version 2, and version 2 with data flow. We're going to use version 2 here for our demonstration. Now the differences between these 3 versions are that version 2 adds a little bit more functionality over that of version 1, while also making some of the tasks that you performed in version 1 even easier. Version 2 with data flow builds upon version 2 by allowing you to create data flows and pipelines without any coding. It's intended to be a totally visual design solution. However, since it's in preview, things are likely to change as bugs are identified and suggestions are made. So we're going to use 2 for this demonstration. As far as location goes, we'll deploy our Data Factory into the East US location. Now what I do want to point out is if I drop down the box here for location, you're only going to see a subset of Azure locations. That's because only a subset of Azure locations support Data Factory. So we'll keep East US here, and then we'll click Create. And what we're going to do is pin this to our dashboard here. And so now we can see our Data Factory has been provisioned. In the next demonstration, we'll create a pipeline using the Data Factory user interface. With our Data Factory deployed, we can launch the user interface and create an actual pipeline. What this pipeline will ultimately do is take data from our blob storage and copy that data into a SQL database. So let's get started on the pipeline creation. To launch the Data Factory user interface, click on Author and Monitor from the Data Factory itself. What this will do is open the user interface in a separate tab. Now remember, you need to do this in either the Edge browser or in Google Chrome. As you can see here, our user interface has popped up, and it's actually a pretty slick looking tool here. So to begin the actual pipeline creation, we'll click Create Pipeline. Now as you can see here, there's a lot going on the screen. My personal opinion is that the Data Factory UI is a little bit too busy. They could probably break this stuff out a little bit better, but it's what we have right now, so let's just go with it. The first thing we're going to do here in this general tab down here is give our pipeline a name. So we're going to give our pipeline a name. We'll call it Copy from Blob. All right, so our pipeline itself is called Copy from Blob to SQL. Now what we need to do is specify an activity that this pipeline is going to perform. So we're going to go under Move and Transform here, unless this is changed. There we go. And we're going to take the Copy Data activity and drag it into our pipeline designer surface here. After dragging the copy data activity to our pipeline designer surface, we need to give our activity a name. So what I'm going to do is I'm going to call this activity blob to SQL. So now what we have is we have a pipeline called copy from blob to SQL. And then what I've done is I named the actual activity blob to SQL, so we can differentiate what we're working with throughout these next few demonstrations. After providing a name for our copy activity, we need to provide a source and a sink. The source is where our data is going to come from. The sink is where we're going to copy it to. The source is essentially going to be our blob storage, while the sink will be the SQL database. So to configure our source, we're going to click on the source tab here. And before we do that, you can see here source has a little 1 superscript, as does sink. And this is telling us there's some activity that we need to do in this section. So we'll go ahead and click source. And what we're going to do here is we're going to create a new data set. That data set is going to be blob storage because we're pulling from blob storage. So we'll select Azure Blob Storage here and then click Finish. What this does is open a new tab for the blob data set. In the general section here, we need to give the data set a name. So we'll call this source blob. After providing a name for our data set, we can see here that connection is asking for some information. So let's click connection here. In the connection window, we're going to create a linked service. Essentially what this is going to do is link the pipeline to our actual blob storage down to the file that we're going to pull into our SQL database. So to do this, we're going to click New to create a new linked service. And then we have to give our new linked service a name. So we'll just call this my linked service. After providing a name, we need to select our storage account. And I'm using my data source 9878 for this demo. And then once we've selected our storage account, we can click Test Connection. After we confirm that we can connect to our storage account, we can click Finish. Now what this is going to do is deploy this linked service that allows Data Factory to talk back to our actual storage account. Once the linked service is created, we're taken back to the page for our dataset settings. From here, we're going to specify the file that we're going to pull into SQL. To do that, we click Browse next to File Path. You can see here it's blank right now. We're going to fill this in by browsing. So we'll click Browse here, and then we'll double-click My Data, which was the container, the input, which was the folder, and then the data text file. After doing so, it fills in this information. Now, once we've specified this data text file, we need to make sure that Data Factory is seeing the file for what it is. So what we want to do is confirm that it sees the correct file format. To do that, we just scroll down here, and we can see under File Format Settings that it indeed sees it as text format and sees it as comma delimited. Now, if the source file uses different rows or columns, what we could do is click on Detect Text Format. What this would do is cause the Copy Data tool to detect the file format and delimiters again. If it still doesn't see them correctly, we could also override them. In this case, we're good. So what we'll do here is we'll preview our data to make sure it's reading the file. And on your screen here, you'll see there are 2 rows in our file, Tom Mitchell and Jen Smith, with 2 properties. We'll close the data preview. And next what we need to do is import the schema. So we'll select schema, and then we'll click Import Schema. And here again, we'll see that the application has detected 2 columns in the source data file. Now, the reason we're importing this schema is so that we can map columns from the source data to the sync data, which is essentially the database. So now that we've imported our schema, what we can do is hop back over to our pipeline and then browse to the source tab. What we want to do is confirm that our source data set is still our source blob, which it is. And then what we'll do is we'll preview our data here to make sure everything still looks good. And it is. So we'll close this out. And then next we'll configure the sync. The sync is essentially the destination where we're pulling this data to. To do this, we click on sync. And again, here you'll notice a little superscript here, 1, telling us that there's some activity that needs to be done. And then once we're in the sync tab, we'll click new to create a new sync data set. Now our sync data set is going to be an Azure SQL database. So we'll just search for SQL. And as you can see here, Azure SQL database is an option. So we'll select it and then click finish. As was the case with all of the other resources that we've deployed so far, we're asked for a name. So we're going to call this SQL dataset. After providing our name, we'll go into the connection tab to create the linked service that allows the SQL to bring that data in. As we did previously for our source, we'll create our new linked service for our destination by clicking new. Now what this new linked service is going to do is it's going to provide the connection string that Data Factory is going to use to connect to the SQL database at runtime. So for this new linked service, we'll give it a name and we'll call this SQLDB linked service. After giving it a name, we have to select our SQL server that we've deployed. And here it's SQL Server 9878. This is the server that hosts the database that we're pulling the data into. After selecting our server name, we select the actual database. Next, we have to specify an authentication type. You have a couple different options here: Service Principal, Managed Identity, or SQL Authentication, depending on what you're using for your authentication. In our demo here, we're using SQL Authentication, so we'll provide the username and password to connect to the SQL server. Once we've provided our username and password, we can test the connection to ensure good connectivity, and we can see here that the connection was successful, so we can go ahead and click Finish to complete the creation of our new linked service. With the linked service created, we have to select the actual table where we're going to pull this data into. So we've got the SQLDB linked service that specifies the SQL server as well as the SQL database. We now have to tell it what table to use within that database. So in the drop-down box for table, we select our dbo.emp. The dbo.emp is a table that was created in the database as part of the setup for this demonstration. After specifying the table, we then have to pull in the schema. So we'll import the schema just as we did on the source information. So what we're doing here is we're pulling the schema in from the database so we can match it up with the source information. Now you'll see here we pulled in 3 columns from our database. We pulled in an ID, a first name, and a last name. So these are the columns that exist in our SQL database that we're going to copy data to. Now the identity column here is a column in the SQL database that isn't going to receive any data from our source file. So what we're going to do here is we're going to delete this column. So what we're left with is first name and last name. So what we're going to do next is configure a mapping. We're going to map the column names from our source data to those in our SQL database. If you remember back, the source data included 2 columns, prop 0 and prop 1. We're going to map those columns to first name, last name in our database. To do that, we're going to go back to our pipeline tab. And first, we want to make sure that our sync dataset is our SQL dataset, which it is. There's no reason that would have changed. And then what we're going to do is click on the mapping tab here. And then from here, we'll import the schemas. And you'll see here that the mapping is seeing prop 0 and prop 1 from the initial source data. And it also sees the first name, last name. And what we're doing here is we're seeing that it automatically configures the mapping for us. And this is based on the order in which the fields were found. So now that we've confirmed that the mapping is in place, what we want to do is validate the pipeline. To do so, we simply click Validate. The message that we receive here tells us that our pipeline has been validated. It tells us that no errors were found. So it looks like our pipeline is good. If we click on the arrows up at the top here, we can see the code for our pipeline as well. With our pipeline validated, we can debug and publish the pipeline. So before publishing our pipeline, we want to debug it. We want to make sure everything runs as expected. Now we know we've done the validation, but we want to actually see the process run and make sure from beginning to end everything works as it's supposed to. So to debug the pipeline, from within the Pipeline tab, we click Debug. And what this does is provide a status of the pipeline in the Output tab down the bottom. It tells us it's in progress at this point. And what we can do is look at the glasses here for details. And you can see here it gives us some information about the duration of the actual process that was run as part of the pipeline. We can see the start time, the duration, how many files were read, how many rows were read, and how many rows were written. So we can close this detail window and see that our debug was successful. Now once the pipeline runs successfully, we can publish it. To publish the pipeline, we simply click Publish All in the top toolbar. Now what this is going to do is publish everything in the pipeline, the data sets, the pipelines, everything that we created in Data Factory. So we'll go ahead and click Publish All. You'll see here we receive a message saying it's published successfully. And at this point, our pipeline is active. It's live. Now there's two ways we can trigger the pipeline. We can trigger it manually, or we can trigger it on a schedule. What we're going to do here is trigger the pipeline manually. To trigger our pipeline manually, and essentially this is to test it to make sure it looks good in a production setting. To trigger this manually, we're going to select Trigger on the toolbar here. And then we get two options, a new or trigger now. We'll go ahead and trigger it now. And it's going to tell us that this pipeline is going to run based on the last published configuration, which is fine because that's what we want. So we'll click Finish. And what this is going to do is trigger the pipeline to run manually. Now what we can do is select the Monitor button on the far left here to view the activity. We can see the manual trigger was successful and it took 19 seconds. Now under Actions you have a few different options. You can view the activity runs and you can rerun the actual trigger. If we click on the View Activity Runs, we'll see the activities that happened as part of this pipeline. We'll see that it was a copy activity type, when it started, the duration, and if it succeeded or not. Then there's other options here, Input, Output, and then we can view details. And the details essentially tell us what we were told before during the validation, is that it's reading one file, 2 rows, and writing 2 rows, and then gives us some information on the duration itself. So let's go back to our pipeline runs here, and we can see we're good. So now that we know that the pipeline run was successful, and that it created the 2 rows in our database, we can now trigger the pipeline on a schedule. So what we're going to do here is set a trigger to run our pipeline every minute until a specified end date and time. To create our schedule, we can click the Author button here, or the little pencil, and then from our Pipeline tab, we can click Trigger. And instead of triggering now like we did when we manually ran the pipeline, we're going to click New or Edit. And then from here, it's going to allow us to add a trigger. So from the Choose Trigger drop-down box, we simply click New. we'll give our trigger a name, and we'll call it every minute. And then we have our schedule type here. A scheduled trigger is a trigger that invokes a pipeline based on a typical wall clock schedule, every so many minutes, every so many hours, etc. A tumbling window trigger operates on a periodic interval. It also retains state. An event-based trigger is essentially a trigger that responds to a specific event. We're going to use the schedule type. And as you can see here, we specify the start date in UTC time. So this is essentially immediately. And for recurrence, we're going to schedule it to run every minute. And then an end date we're going to specify. And what we'll do here is we'll select our day. And then we'll schedule it just to end a few minutes from now. And we'll apply it. Now once we specify the date and time here, we can see that it's activated. And what's going to happen here is we're going to activate this new trigger once it's published. So we'll click next. And before we click finish here, we're getting a warning telling us make sure to publish the trigger after clicking finish. So we'll finish this. And then from here we'll click publish all. And this is going to deploy our changes to our data factory pipeline. So at this point, our scheduled trigger is now configured. And as you can see here, it's deploying. So our changes have been published to our pipeline. So what we're going to do here is click on monitor over on the left, and then we'll refresh this every so often, and we should see the new activity showing up within the monitoring section here. And already we're seeing the first triggered pipeline run, and it tells us it's triggered by the every minute trigger. So as you can see, what we've essentially done is create a mini data flow using Azure Data Factory to pull data from Azure Blob Storage to a SQL database. We've configured that pipeline to pull in data manually, and we've also configured it to run on a schedule. In this brief lecture, I want to touch on what database services are available in Azure. Getting back to our previous data flow example of the casino, the database service is the source of information. Player info from the floor's slot machines is continuously written to the backend database. In turn, the data from the database is then fed in as the source for the casino's overall data flow. That said, in other scenarios, the database service can serve as some intermediary step in the data flow process, or it can even serve as a data mart. There are many different database services available in Azure. They are available as both platform as a service offerings as well as database as a service offerings. For example, Azure offers services such as Azure SQL Database and Cosmos DB. Because Cosmos DB is a NoSQL implementation, it's a good fit for data such as documents and graphs. Conversely, because Azure SQL Database is a more traditional relational database, it's better suited for relational data. There are also several infrastructure as a service options available as well. You can simply run a database instance within an infrastructure as a service virtual machine if platform as a service isn't your thing for some reason. So when designing a data flow, you may find yourself splitting between or among multiple models or even platforms due to the data that needs to be processed. In this lecture, I want to talk a little bit about HDInsight. Azure HDInsight is an offering that's built for big data analysis. It's a fully managed open source analytics service that's been designed from the ground up for enterprises. It's a cloud service that allows for fast, easy, and cost-effective processing of large amounts of data, and it supports many scenarios, including ETL, data warehousing, machine learning, and even IoT. HDInsight is a solution that's going to work in virtually all of those scenarios. It also supports multiple cluster types, including Hadoop, Spark, and more. The role that HDInsight plays in a data flow is the engine, if you will. It's going to power transformations that need to be completed. Using HDInsight solutions offers the ability to seamlessly integrate with many different Azure data stores and services. Such services include things like SQL Data Warehouse, Azure Cosmos DB, and Data Lake Storage. HDInsight also integrates with other offerings such as blob storage, event hubs, and Data Factory. Because HDInsight cannot be paused, you might just want to create an instance of the service when some sort of analysis or transformation work is required, and then delete it when the work is complete. This would obviously be part of some sort of automation process and would typically be something that you do when processing data infrequently in batches. When designing a data flow that incorporates an HDInsight cluster, the programming languages that you use in other parts of the data flow are going to be dictated in part by the cluster type that you deploy. For example, if you use Spark, you might consider using Scala, Python, Java, etc. That being said, it takes us back to one of the initial questions we touched on earlier in the course. What skill sets do I have in-house? When designing a data flow that includes HDInsight, be sure to choose technologies and services that are supportable by your staff. Azure Databricks is an alternative to HDInsight. It's an Apache Spark-based analytics service in Azure that allows you to deploy data analytics and artificial intelligence. It allows you to pull together data at virtually any scale. You can then obtain data insights via features such as analytical dashboards and operational reports. With Azure Databricks, you can transform data into actionable insights via advanced machine learning tools, allowing you to combine all kinds of data at any scale. It also allows you to build and deploy custom machine learning models. As part of a data flow, Azure Databricks offers you the ability to deploy an easily auto-scaled Spark environment within minutes. It supports languages such as Python, Scala, R, and SQL, in addition to several deep learning frameworks and libraries such as TensorFlow and PyTorch. Its native integration with Azure AD and other Azure services allows you to build a modern data warehouse complete with machine learning as well as real-time analytics. The image on your screen does a good job of depicting the role that Databricks plays in a typical data flow. It fits into the transformation and analysis stage of the data flow. Once the ingested data has been processed through Databricks, analyzed and transformed, it can then be served up via services such as Power BI and other Azure analysis services. What Databricks does essentially is provide you with an analytics platform that can be used to apply intelligence to data, which in turn provides valuable insights into the collected data. Moving forward, you can expect to see more and more modern workflows leveraging Azure Databricks. When designing data flows, Azure SQL Data Warehouse is likely to be situated at the end of the line, where ingested and processed data is stored so that it can be later analyzed. When processed data is ready for analysis, SQL Data Warehouse uses Polybase to query the big data stores where the processed data lives and uses standard T-SQL queries to pull the data into SQL Data Warehouse. This scaled-out version of SQL Server focuses on providing enterprise data warehouse functionality by leveraging massively parallel processing, or MPP. While it does provide SQL compatibility, Enterprise Data Warehouse doesn't do everything that SQL can do. For example, Azure SQL Data Warehouse doesn't support foreign key constraints. That said, it's not really meant to be used like SQL Server is. What SQL Data Warehouse does is store data into relational tables using columnar storage. Doing so vastly reduces the data storage costs while improving query performance. Data that is stored in SQL Data Warehouse can be analyzed at massive scale. When compared to other traditional database systems, SQL Data Warehouse analysis queries finish in seconds or minutes instead of hours or days. When designing a data warehouse with Azure SQL Data Warehouse, begin by loading data into a service such as Azure Data Lake Storage or Azure Blob Storage. From there, you'll want to use Polybase to load the data into a staging table in SQL Data Warehouse. Next, choose a table distribution strategy. You can configure distributed tables or replicated tables. A distributed table appears as a single table. However, its rows are actually stored across 60 different distributions, and they are distributed with a hash or round-robin algorithm. A replicated table, however, makes a full copy of the table accessible on each compute node, of which there can be as many as 60. By replicating a table, you remove the need to actually transfer data among the compute nodes prior to a join or aggregation. Replicated tables work best in cases where the table size is less than 2 GB compressed. Next, you'll need to index your table so it can be read quickly. You can leverage one of 3 types of indexing depending on your needs. The heap type of index is good for staging and temporary tables, as well as small tables with small lookups. A clustered index is better for tables with up to 100 million rows and for tables with more than 100 million rows, but with only 1 or 2 columns that are heavily used. A clustered column store index, or CCI, is best for large tables with more than 100 million rows. You might also want to partition a table when a large fact table is involved. A large fact table would be one with more than 1 billion rows. In almost all cases, the partition key should be based on date. It's important to note, however, that you do not over-partition, especially in cases where you are using a clustered column store index. While it's not necessary, incrementally loading the data minimizes disruption to business users. If you do choose to incrementally load data, ensure that you allocate larger resource classes to loading your data. Microsoft recommends using Polybase and ADF v2 for automating ELT pipelines into SQL Data Warehouse. It's important to remember that if you know in advance what the primary operations and queries are going to be run in the data warehouse, you can build a design that prioritizes the data warehouse architecture for such operations. In this lesson, let's take a 30,000-foot view of the modern data warehouse and how data flows through it. Source data can come in many forms. It can come from logs, files, and even media. And it often comes from many types of devices and applications. As this data comes in, whether it's structured or unstructured, it needs to be combined. For this process, you can leverage Azure Data Factory. As such, Azure Data Factory is essentially the engine that provides the overall flow control. It acts as the orchestrator in the entire process because it helps ingest all the different types of data. Once it's done with ingestion, it stores the data in Azure Blob Storage. Doing so offers the ability to maintain data in its raw format for long periods of time due to the low cost. What this does is allow you to go back later and run new or even different translations on the data to get new answers to new questions that crop up. Next in the flow comes Azure Databricks. Choices include Python, Scala, and Spark SQL, among others. Alternatively, you could use HDInsight instead. Either offering, however, provides a scalable analytics capability that's used to clean and transform the data, which is then stored in the SQL Data Warehouse. Whether it's Databricks or HDInsight that does it, the data is going to be cleaned up so it follows a schema that can be used to get business answers from via analysis. To perform the analysis, you can use Azure Analysis Services. To facilitate the querying of the completed analysis, you can use a service such as Power BI. By leveraging something like Power BI, you can get stuff like operational reports and analytical dashboards. It essentially leverages analysis services under the hood. It will then query Azure SQL Data Warehouse. As you can see, in such a design, data flows in from its original sources. It's then stored and cleaned up. Next, the data is remodeled and translated before being stored in the final analysis format. Analysis is then run against the data. This overall process is a typical way in which you would pull together several different components to design a modern data warehouse. I hope you've enjoyed learning about data flows and the components and thought process that goes into designing them. Let's review what you've learned. In this course, you learned about data flow basics. You learned about common data flow scenarios along with the data lifecycle. You were then taught what goes into determining data requirements and the benefits of data flow in the cloud. Later in the course, you learned about the process of designing a data flow, including the assessments of data flow requirements and Azure Storage options. You learned about the role that Azure Data Factory plays, as well as the role that Databricks plays. Next, we covered core components of a data flow, including Azure HDInsight and Azure SQL Data Warehouse. To round out the course, after learning about all the key components that constitute a data flow, you learned about what a typical modern data flow looks like. To learn more about data flows and how to design and document them, you can and should read Microsoft's published documentation. Be sure to also watch for new Microsoft Azure courses on Cloud Academy because we're always publishing new courses. Please give this course a rating, and if you have any questions or comments, please let us know. Thanks for watching and happy learning.